So we're going to start with the two pieces of advice that we almost always give, which is number one, you need to do problems. So as I've said, I wrote these problems, but I'm not the one who wrote the problems on the exams. So it's good to look at other problems and sort of say, okay, what are some other ways that I might see these things? So where can you get other problems? Well, there was a review last semester that was very similar. You can look at recent exams, old exams, and you can look at the quiz banks. In fact, the quiz banks have tons of old problems. And so there's lots of old problems to look at. And one of the things that you learn from looking at problems is you learn to sort of recognize certain patterns. And that's what doing problems helps you to do, is you recognize, aha, when I see this type of phrase, this is the right tool to use. And the other thing, of course, is take care of your health. We already mentioned to not lick anything, but go out, get plenty of rest, go out, take a walk. It's beautiful weather this upcoming week. I think you should enjoy the sunshine. I don't think it's the best thing for your health, physical or mental, to stay locked inside for the next 5 days. You should go outside. You should get some fresh air. You should get plenty of sleep. You should eat good food. And the reason it being is we want you to come into the test as your best self. We want to know, can you do math when you're in your best situation, not when you're sleep deprived, hungry, and well, all those terrible things that could go with that. So let's get into it. So we start with somewhat of an artistic problem. Number one, sketch the domain of the function f of xy equals the square root of y minus x plus the square root y plus x divided by the natural log of 2 minus x squared minus y squared. Now, on an exam, if we ever give you a problem for sketching, we'll actually give you a grid. I didn't put a grid on here, but I just want you to know that you're not going to have to sort of guess or make your own grid. We will give you a grid. And the reason we do that is it makes it easier for us to grade. But it also helps because you'll have something to go with. Now, whenever you see a problem about sketch domain, really this is testing you on a couple of things. The main thing is the domain. So we sort of say, okay, we need to understand where are our problem areas. Well, what do we need to avoid? We need to avoid divide by 0. That's sort of the big one. We need to avoid square root of a negative. Can't take square roots of negatives. And we need to avoid a natural log of anything that's less than or equal to 0. So natural log is even more restrictive than square root. Because with square root, 0 is okay. But with natural log, no, 0 is out. And basically, as long as you avoid these problems, you're fine. So when you see a problem about domain, you start saying, okay, well, let's go through my potential problems. All right, we'll go through these. We might as well do them in order. There's really no reason not to. So divide by 0. You look downstairs and you ask yourself the question, well, when can the denominator equal 0? Well, natural log of what is 0? Natural log of 1. Okay, so that says 2 minus x squared minus y squared equals 1. That's trouble for us. Or x squared plus y squared equals 1. So that's the unit circle. We need to avoid that circle. But as long as we avoid that circle, we're not going to divide by 0. We might have other problems, but not the divide by 0 variety. Okay, well, next one. Square root of a negative. Well, we see we have 2 square roots, so we just got to do them both. So what we need y minus x, and now we can think of, do we want to say what do we want to avoid or what do we want to be, where are we okay? So in this case, let's just sort of say where are we okay? Y minus x greater than or equal to 0 and y plus x greater than or equal to 0. Now if we think about this, this says we need y to be greater than or equal to x. That's the first equation, just moving the x across. And the second equation says that y has to be greater than or equal to minus x. Now, what does this look like? Well, y greater than or equal to x. So y equals x is this line. If I want to be greater than or equal to x, well, that says I should be above the line. So I should be in here. Y greater than or equal to minus x. Well, y equals minus x is a line that goes in the other way. And I want to be above that line. Means I want to be in there. And now, well, I need to actually be in both. So the square roots are telling me I need to be in this sort of V region upstairs. That's what the square roots say, is I have to be up there. All right? And don't forget, we're going to have to avoid that. We're going to combine these things. So we have to be up here and avoid that, but we still have one more thing to do. So our last part of our puzzle, whatever we take in the natural log, we can't take it if it's less than or equal to 0, which means the inside has to be positive. So 2 minus x squared minus y squared has to be positive. What's another way for us to write this? X squared plus y squared is less than 2. Now what is that? It's a circle. What's our radius? Square root of 2. Yeah, not 2, square root of 2. And notice I'm putting a dashed line. Dash indicates that's bad. We don't want that. Because when I put a solid that says, yes, we're okay, that's when you have an equality. Dash is strict inequality. Now, are we inside or outside? Yeah, we're on the inside. So you know what they say. And one inequality you're in, and the next you're out. All right. So we want to be inside that circle. So now what we do is we sort of piece all these things together. So we draw ourselves a grid, and we start saying, well, I've got to be up in the V, so I'm going to draw the V shape momentarily. I've got to be inside of this circle, so I'm going to do a little dashed circle of square root of 2. And hopefully that looks like a circle of square root of 2. I also am going to draw my dashed circle for x squared plus y squared equals 1. And so square root of 2 is about 1.4. So it's not really halfway in between. It's some portion in between. Something like that. All right, now what do we shade? Well, we got to be inside the big circle. This little circle here is not really a boundary, it's just saying avoid that. So we're inside the big circle and up above the V. So our region is this part right here. So it's sort of a 1/4 of a pie of some sort. If we were going to be really precise, do you see where the circle intersects with the line? What should we draw there? So where this dashed circle intersects with the solid line, what should we really draw there if you were being super precise? It'd be an open point. Yeah, if you have one problem, that rules you out. So there's actually should be open. Open points are just a fancy way of saying we don't include that. So that's the answer. There you go. And again, if this were on an exam, you'd have a grid, so it would be much easier for you to draw things. And we're not looking for perfection, but usually we're going to ask you to draw things like circles, lines. Those are things we think you can handle. Occasionally we have gone out and said parabolas, but yeah, that's about as crazy and wild as we get. So, all right, number 2. Sketch and label. Oh wow, more drawing. This is great. The level curves for the function h of xy equals x squared plus y over x for some various values, k equals 0 to 4. So again, if we ask you to draw this, and we have asked people to draw level curves. In fact, I think last semester there was a question about drawing level curves. So we're going to sketch and label. So all right, we're going to draw level curves. Well, when we say level curves, what do we think of? Or what does that mean? Okay, good. I like how we're deep in thought. We're like, wow, level curves is such a profound thing. It's hard for me to express my love for level curves. Well, I'll attempt it. So level curves is, we want to set, where does the function equal a certain value? If you're familiar with topographical maps, it's like, okay, an elevation. Or if you ever see weather maps, sometimes they do this where it's like, okay, in this part of the country, you're this temperature, this part, you're another temperature. And then they have lines for like, okay, here's where you see different parts. So level curves is when you set your function, in our case, h, equal to some constant k, and then this describes a curve in the plane. So that's what we're drawing, is level curves are curves in the plane which correspond to a fixed output for the function. So we're going to do this for this particular function for different values, 0, 2, 4. Now, we should make a note here. This function has sort of an interesting thing happening. What's bad about this function?
X can't be 0.
Yeah. See how we have that x downstairs? So we're just going to make a little note here. X is not 0 for our domain. Now, that just says that technically anything which involves 0, we would put a hole in it. But I think it's going to become clear what happens when we do that as we go through this example. So let's work through our process. So first off, what we do is we take our function, x squared plus y over x, and we set it to each one of these values. So equals 0, x squared plus y over x equals 2, x squared plus y over x equals 4. And now we just sort of start doing our manipulation. We're going to say, look, x is not 0, so don't worry about it being 0 for right now. And, well, we work it till we get to something we're more familiar with. So in this case, let's multiply through by x on each one of these and see what we get. We get x squared plus y equals 0. And here we get x squared plus y equals 2x. And here we get x squared plus y equals 4x. This is looking pretty good. I think if we push one more, we might see what we have here. So in the last thing to do is let's get y by itself, because there's just a single y. So y equals minus x squared. Y equals 2x minus x squared. And this would be y equals 4x minus x squared. So that would be what would happen if we were to just rearrange this equation. Because that's what you do when you're trying to draw level curves. You set your function equal to whatever height you're at, rearrange the equation, and life is at least manageable. Let's talk about these curves. What curves are we seeing here? These are all parabolas. So we're going to draw a bunch of parabolas. And we don't have to be super precise, but we have to be reasonable. So let's go through and sketch our picture. I'm just going to put a little dashed line down here. It's kind of hard to see, but there's a dashed line. Just as a reminder, x can't be 0. Let's talk our first parabola. Y equals minus x squared. Again, we just need it to be roughly the right kind of shape. What does that look like? Yeah, it's just the normal parabola we're used to, y equals x squared, but now going down. So that one we're pretty comfortable with. Hello, parabola, my old friend. Okay, so there's that parabola. Let's talk about the next one. Y equals 2x minus x squared. That one is not so bad, but not exactly, off the top of our head we might say, aha. But let's talk about this parabola. Which way do we open, up or down? Down, because of the x squared has a negative coefficient. Okay, that's good. Let's talk about the x-intercepts. Where do we hit the x-axis at? At 0, yes, and where's the other one?
2.
At 2. So we're going to hit at 0, which means we'd actually hit at the same point, and over here at 2. But other than that, essentially it's like we've taken this, because it's still a minus x squared. So what we've done is we've really taken it and shifted over. So it's other. Oh, that's not that's a closed dot. And so it's still the same shape, just moved over. Okay, so it's this, and then we translated it over some. All right. Well, Okay, how about, oh, and we were supposed to label these, and I didn't label them yet. Let me label them. So this, which one, how do I label this? Yeah, this is the 0 one. Then the sort of the bluish, blue-green one, that's 2. I'll put it there. And the last one, y equals 4x minus x squared. Okay, similar shape. Parabola, opening down. Where do I hit the axis at? 0 and 4. So over here. But other than that, I mean, it's really the same shape, just, again, translated. So you end up with something that looks like that. So that's what the level curves look like. It's the parabola just moved around. Now, one of the things we could tell, and this is not part of the question, but there was a question from a few semesters ago which said, well, what happens as we approach 0, 0? Well, it's terrible because you'll see almost every level curve passes through 0, 0. So at 0, 0, it thinks it's almost all values simultaneously, which is really bad. That's a different question. That would be if we were talking limits. All right. Oh, I'm sorry. I took it off really quick. Any questions about level curves? All right. Good. Number 3. Find all second-order partial derivatives of this following function. G of x, y, z is z cubed e to the x plus the natural log of absolute value of x squared plus 1y cubed. The absolute value really, don't worry about that. It doesn't really do anything for log. Okay, so don't panic if you see absolute value attached to log. Now, this is not meant to be a hard problem, other than it's going to take a while. This is just checking, do we know how to do partial derivatives? How many first-order partial derivatives are we going to have? We're going to have 3 because we have 3 variables. So when we do first-order partial derivatives, we're going to have 3. Now, you might say, Steve, whoa, hold on a second. This is asking for second order. Why are you bothering? Well, if you're going to get to second order, you first have to do the first order. So yeah, we got to do 3. So we'll do those in a second. So we're going to have gx, gy, and gz. And by the way, there's lots of notations for partial derivatives. If you prefer the one with the partial symbols, good on you. That's great. It seems to take a lot longer to write all those, and especially once you get to second derivatives. But yeah, you can write whatever notation you like. Now, how many second-order partial derivatives will we have? Okay, I've heard 3. I've heard 9. Anybody want to take the average? Yeah, okay, let's say there's 6. I don't know. How many? Well, let's figure it out. Well, first off, does it matter which order we take? In other words, gxy versus gyx, do I need to do both of those? No, because we're in the class where it doesn't matter. Now, that's not to say that there will always be the same, but it's going to say that any reasonable function, which means any function we could come up with that wouldn't get us tarred and feathered, they will be the same. So let's just list them. So gxx, what would be next? gxy and gxz, okay, and then gyy, and then gyz, and then gzz. And that looks like 6. And did we miss any? I don't think so. So we'll be here for a few minutes. That's okay. That's okay. Now, one of the things we're going to do before we start this problem is just to pause for a second and say, anytime you're asked to take a derivative of something, or an integral, but it works in derivatives as well, you should always ask, is there anything I can do to make it look simpler? Is there anything we can do to make our function look simpler?
Should we distribute that y cubed? Should be the natural log.
Well, see how we have log, and there's 2 things multiplying? What can you do with that? You can turn that multiplication into addition. So natural log of x squared plus 1, and natural log plus natural log of y cubed. What's another way to write natural log of y cubed? Yeah, 3 natural log of y. Okay, and now we're just going to be patient. And this is practice. This is practice. Okay, so g sub x. That means we're going to take the derivative. X is our variable. We're treating all the other variables as constant. So what do we get? C cubed e to the x. Anything else?
Plus 2x over x squared plus 1.
2x over x squared plus 1. Anything else?
No.
No. The 3 log y disappears. Okay, g sub y. There's no y? There's no y? 3 over y. Ooh, our favorite derivative so far. G sub z.
3z squared e to the x.
3z squared e to the x. Anything else? No? Good. Now we're done. Okay, gxx. So we're going to come up to g sub x, take derivative of that with respect to x. Well, first term shouldn't be too bad. What's that? Z cubed e to the x, because derivative of e to the x is e to the x. Now 2x over x squared plus 1, that takes us back. Wow, man. Calc 1. Good stuff. What rule do you want to use? Ooh, a product rule. Interesting. Yeah, because you can think of 2x over x squared plus 1 as 2x times x squared plus 1 to the minus 1. And then you can do a product rule. So a lot of people think it's quotient rule. It's really either. It's whatever you're comfortable with. But when you take that derivative, what do you get? Well, if we did a quotient rule, you take the bottom, x squared plus 1 times the derivative of the top, minus the top, times the derivative of the bottom, all over the bottom term squared. Now, you might say, do we need to simplify? Well, there's 2 times when you should simplify. The first time you should simplify is if it says simplify. Okay, so that's one of them. The other time you should simplify is if you have to do something else with it. If the answer is no, and you're told you don't have to simplify, then just stop. We have seen a lot of people have right answers and then realize, like, I have time, let me simplify this. It did not turn out well. Okay, all right. G sub x, y. Now this one we actually have a choice. We can come up to g sub x and take the derivative with respect to y, or come up to g sub y and take the derivative with respect to x. Which one do you want to do?
Gx, y, well, if there's no y.
Yeah, they're actually both easy because in either case, you get 0. All right, how about g sub x, z? So again, you can think of coming up to g sub z, taking the derivative with respect to x, or g sub x and take the derivative with respect to z. You'll get the same answer. What will that answer be?
3z squared e to the x.
3z squared e to the x. G sub y, y. You get 3 over y squared, because you can think of 3 over y as y to the negative 1. G sub y, z. 0. Oh, these are great. These aren't so bad. We should put more of these on the test. G sub z, z. 6z e to the x. Okay, and that's it, because we were asked to find them, and there they are. They're all there. Good. Good. All right. Well, number 4. This comes from a really old exam. This was back years and years ago. Consider the surface z equals x squared plus y squared. We actually like that surface. It's a very nice surface. It's a bowl. And it works really well. And then it says, part A. Find the tangent planes to the surface at 1, 2 and 2, negative 1. So, let's talk about the tangent plane. So what we have here, this is a special case where we have z is a function of x and y. Now when we talk tangent planes, we're going to do tangent planes to 2 different types of things. So this is the first situation when I have z as a function of x and y. Then the way I like to remember the tangent plane is in the following form. So I'm going to have my function at my point AB, and so AB is where I'm taking my tangent plane at, plus the partial derivative with respect to x at a comma b times x minus a plus the partial derivative with respect to y at AB times y minus b. So that's the generic formula for the tangent plane at any point AB. So that's the one I'm going to be using. So in our particular case, our function is the x squared plus y squared function. So let's work through what happens. So for part A, when we have the point 1, 2, well, that says our z, our tangent plane, f of 1, 2 plus, and then we have to have f sub x at 1, 2 times x minus 1 plus f sub y at 1, 2 times y minus 2. That's what our tangent plane will be. Let's figure these numbers out. F of 1, 2, what would that be?
5.
It'd be 5, 1 squared plus 2 squared. Okay, this one we'll do a little bit in our head. So our function is x squared plus y squared. What's f sub x? 2x, and then if I plug in x equals 1, y equals 2, that becomes 2, because it's 2x, but x equals 1, so 2 times x minus 1. F sub y? So our function is x squared plus y squared. Take the derivative of that with respect to y, we get 2y. Plug in 1, 2, that gives us 4. Y minus 2. Okay, so that says that our plane is z equals 5 plus 2 times x minus 1 plus 4 times y minus 2. All right, good. Now that's one of our two planes. So we did the 1, 2. The 2, negative 1, very similar. So it's the function at 2, negative 1 plus f sub x at 2, negative 1 times x minus 1 plus f sub y at 2, negative 1 times y minus 2. When I plug 2, negative 1 into the function, what comes out?
Same thing. 5.
Still 5. F sub x at 2, negative 1? 4 times x minus 1. Sorry, x minus 2, excuse me. Oh, that should have been a 2. That should have been a plus 1. I am so sorry about that. Okay, but that's why we have the chance to go back and check our work. So we can make sure we get all the points. That's our goal. Got to get all the points. Well, except for 4 problems. But we want to get all the points on these problems because we're saving our drops for later on. Or maybe we already used them. But, okay. F sub y at 2, negative 1. What would that be?
1 times 5.
Well, so remember, our function
Plus 2.
is x squared plus y squared. Our f sub x is 2x. Our f sub y is 2y. So f sub y at 2, negative 1 will be negative 2. So we end up with the plane z equals 5 plus 4 times x minus 2 minus 2 times y plus 1. Okay, so that's part A. So that was not so bad. Now it says part B. Find the point so that the tangent plane at AB is perpendicular to both planes found in part A. Oh, okay. So we're going to get to do a little bit of fun little thinking here. All right. Well, it says, recall, two planes are perpendicular if their normal vectors are perpendicular. Okay, so what can we do here? Well, let's start thinking. What are some ideas we can use to approach this problem? Yeah?
Use A and B to create like a general formula and then have the dot product equal to 0.
Okay, so we can create a generic formula. So let's do that. That sounds good. And then we're going to grab the normal vectors, and then we're going to take the dot products, and hopefully it will become beautiful. We'll find out. All right. So our generic form, I'm just going to come up here. It's z equals a squared plus b squared plus our f sub x will be 2a times x minus a. And our f sub y will be 2b times y minus b. Okay, so that's our generic. There's our plane. And we just need to solve for a and b. We don't actually have to give the formula for the plane. Now, if we clean this up, well, I don't know if it's really cleaning it up, but if you expand this, you get 2ax plus 2by, and you'll see you have a minus 2a squared and a plus a squared. So that's minus a squared. There's also a minus 2b squared and a plus b squared, so that's minus b squared. Now, if we're thinking about the normal vectors, are we in a good place to grab the normal vector with this plane? And if we're not, what should we do? Okay, I will suggest that the answer to the first question is no. We are not in a good place to grab the normal vectors. Not yet, but what can we do to be in a good place?
We're going to use the points that we made, or using 5, 4, negative 2, and use those.
Well, we will go back to use those other planes. So, generally speaking, when we're talking about planes, we want them in the following form. Our ideal form is ax plus by plus cz equals d. And then, if we have a plane in this form, what's our normal vector? Yeah, it's the ABC. So that's the best form, is when you have all the variables on one side. Right now, we have one variable on the other side and then two on the right side. So we need to move one of them around. It doesn't matter which one. Which one do you want to move?
Z, I guess.
We can move the z, right? So we get that 0 is equal to z minus 2ax minus 2by minus a squared. Oh, factor that out. Minus a squared plus b squared. And by the way, let's just do something similar up here. So the first one, if I move the z across, wait a second. I did terrible math here. This should be minus z plus 2ax plus 2by. Okay. Check your work. You never get past making dumb mistakes. You know, I thought I left making dumb mistakes many, many decades ago. But I discovered, nope, still dumb. So I checked my work. So, all right. So I'm going to come up here. I'm going to move that z across. So that's still a minus z. Then I have a 2x and a 4y. So plus 2x plus 4y. And then if I group my constants, I have a 5 minus 2 minus 8. So that's 5 minus 2 minus 8. That's negative 5, yeah, right? Because it's like 5 minus 10. So minus 5. And then the last one, do the similar thing. I move that across. I get minus z. Then it'll be plus 4x minus 2y. And then my constants, let's see, I have a minus 8 and a minus 2. Oh, it's actually still 5 minus 8 minus 2 is still minus 5. So, our three normal vectors, well, the first one, minus 1 comma 2a comma 2b. The second one is minus 1 comma 2 comma 4. And the last one is minus 1 comma 4 comma minus 2. What do you mean? Ooh! Those are really big commas. Huge commas. The biggest commas you've ever seen. Yes. Thank you. All right. So, last thing is, we want this vector here, this normal vector needs to be perpendicular to these other two. So, how do we know when two vectors are perpendicular? Dot product is 0. So, what do you get? 4a plus 8b plus 1 has to equal 0. And then we get 8a minus 4b plus 1 has to equal 0. And now we were like, wow, this is familiar. We do this a lot. 2 equations and 2 unknowns. Our bread and butter. All right, so what do we need to do to finish this up? Bring it home.
You
Do what?
Use algebra.
Use algebra. Yes, what a great thing. How lucky we are. You know, it's kind of sad to think that this is one of the last math classes you might take. There's so much algebra left for you to do. Oh well. Hopefully in your future classes you'll still get to do some. So here's the kind of algebra I like to do. I like to find ways to combine them to get cancellation. So for instance, I see that minus 4b. So if I were to multiply the bottom by 2 and then combine them together, that would be 4 times a and 16 times a, which would make that 20 times a, 8 times b and minus 8 times b, which would be 0. And then you'd have a 1 plus a 2, which is a 3. So 28 plus 3 equals 0. Well, that's good news. That tells us we subtract 3 divided by 20, that a should be negative 3 over 20. What about b? Well, we'll do something similar. But now, for round 2, we won't multiply the bottom one by 2. So we'll cross out our intermediate work. Let's multiply the top one by minus 2. We can do that. If we did that, what happens to the a's? They cancel out. Then you get minus 16b minus 4b, which is minus 20b, minus 2 plus 1, minus 1 equals 0. So what does that say about b? b will be negative 1/20. And there's our answer. Good, good. Now what is this testing? Well, it's testing a couple of things. Some of the things which are a little bit a callback to the first test, but not too bad, namely about when are things perpendicular. But what we're really testing here is, do we understand how to make tangent planes? Because that's an important thing. You can be pretty confident that somewhere on this exam, possibly more than once, you will be called upon to make a tangent plane. So be ready for when that time comes. In fact, let's do it again. Find the tangent plane to the surface x squared y plus xz cubed equals y squared z squared plus 1 at the point 1, 1, 1. Now you'll notice this is not the same setup as before. In the last problem, we had z as a function of x, y. We don't have that anymore. And even if we wanted to, it would probably be a lot of work and make things worse if we tried to make z as a function of x and y. As you'll notice, there's 2 different places where z shows up. So solving for z means we'd have to solve a cubic equation, which there is a way to solve it, but it is, this is a somewhat technical term, unpleasant. So you don't want to do it. So we're not going to do it. So instead, we're going to say, aha, there's a second way to do tangent planes. So here's the second way to do tangent planes. If you ever find yourself in a situation where you have some really strange function of f of x, y, z equals k. K is a number, and this function can be as unpleasant as you want. Doesn't really matter. Then what you can do is you can find the tangent plane to this situation. So what's happening here is that this is actually, there's a couple ways to think about it. One way to think about it is a level surface of some function, but really it's a surface in 3-dimensional space. So the key here is always the normal, see, because the point is given. So, and here's what you do. The normal vector is the gradient of the function at whatever point you want. So if you can remember that, then these types of problems are very easy. Well, almost. There's one catch here. Let's be careful. Are we in the state where we can take our gradient? Not yet. What's wrong? Yeah, see how it's not some function equal a number? So we got to do a little bit of algebra. So x squared y plus xz cubed minus y squared z squared equals 1. Now we're in our good state. This is our function. of 3 variables, x, y, z. So, what's our next stage? Take the gradient. Yes. All right, so this is our first time taking a gradient. It won't be our last. So, the first entry, what does that correspond to? It's f sub x, right? It's the derivative with respect to x. So, coming along here, when we take the derivative with respect to x, what do we get? Two xy plus z cubed. And there's no x's, so we're done with the x. The second entry, that's the derivative with respect to y. What do we get when you take the derivative with respect to y? And that's a 2 in case you're wondering about my handwriting.
X squared minus 2yz squared.
X squared minus 2yz squared. Last entry is derivative with respect to z. 3xz squared and minus 2y squared z. All right, and we don't worry about the 1. It doesn't matter. If it was a 1, if it was a 0, if it was 100, doesn't matter, and we don't take any derivatives, it's just there. What's our next step? Plug in the point. So, gradient of f at 1, 1, 1. So, the nice thing is, 1, 1, 1 is easy to evaluate for polynomials. So, what are the numbers here? 3. Negative 1 and positive 1. All right. Now, it's very important that we make sure we answer the question that was asked. In our case, the question was, what's the tangent plane? We're after that. Are we done with our problem?
No.
Not yet. But we got the hard part. The normal is almost always the hard part. And if we think back, so we should think of our generic formula for a plane. That's ax plus by plus cz equals d. We found the ABC. So we can start writing our answer down. 3x minus y and plus z. Now the only question is, what goes over here? So, what haven't we used yet? We haven't used the point. So this one doesn't matter. But this point matters. So, what you do is you plug your point in. You get 3 minus 1 plus 1, also known as 3. And that's the answer.
If we wanted to just remember one equation for tangent planes, how would we adapt the one that's listed?
You only want to remember one equation for a tangent plane? Oh! I thought people love memorizing equations. Okay, if you can only remember one equation for a tangent plane, memorize this one. And so why is this one better? Because what you can do is if you have a function z equals f of x, y, what you do is you say, okay, here's what I'll be sneaky, I'll move that z across. Then you get your 0 equals minus z plus f of x, y. And now, there's your function of x, y, z, and you're ready to go. And you can.
The last problem too, if we just move that z over.
Yep. Yeah. So this is the more general one. So if you can only remember one, memorize this one. But you're young. You still have neurons left. I believe in you and your ability to memorize 2 things simultaneously. So I am asking for a lot, but well, then we need to start making songs for these things. Well, we'll have a song later on, I suspect. Okay, number 6. So, given that g of x, y, z is a differentiable function at 1, 3, 2, we're going to find the gradient of g of 1, 3, 2 using the following information. So this question is about gradients, and there's a bunch of information here. The directional derivative at the point 1, 3, 2 and the direction of another point is 0. The directional derivative of the function at the point 1, 3, 2 in the direction of a different point is also 0. That's okay, all right. And the direction of g of the function at the point 1, 3, 2 in the direction of a third point is positive. That's not a lot of information to go off of. And the magnitude of the gradient is 22. Okay, so what's being tested here? Let's just actually face up to what's happening. This is testing us on, do we understand the gradient and directional derivatives? And gradients are like super important. So we should be ready to see gradients and or directional derivatives. So let's talk about a couple of things. First off, let's talk about directional derivatives. If I'm looking for a directional derivative, so I'll use our notation. It's kind of a dense notation. Directional derivative. So the D stands for derivative. The U is what direction. We think of that as a unit vector of the function f at a point P. I probably should have used G, but okay. Live and learn. Equals, do you remember what the formula says to do? Yeah, the gradient vector at that point dot U. So directional derivatives are talking about gradients dotting with direction vectors. Now, you'll see here, this says the directional derivative is 0. So that came out of a dot product being 0. When I know that the dot product of things are 0, what is that telling me? That I have some perpendicular directions. So let's look at these directions here. What's the direction from 132 to 442? And I don't need to have a unit vector. I just need a direction. Any direction should do. How do I find the direction that goes from 132 to 442? Yeah, you say this is my start and end. So I take my end values, my start values in each entry. 4 minus 1 is 3. 4 minus 3, 1. 2 minus 2 is 0. Another way to think about it is how much did each entry change? The first entry had to change by 3, the second entry by 1, and the last entry didn't change at all. Okay, come to my second one. This is going to be another direction which is perpendicular. Okay, so what's the direction from 132 to 410? Yeah, so I look at how much I changed. I changed up by 3, then I went down by -2, and then I went down by -2. All right, so those are two directions where my rate of change is 0, which means that both of those directions have to be perpendicular to my gradient. Because look at the directional derivative. That's the dot product is 0, means they're perpendicular. Okay, so we have that the gradient is perpendicular to 310. And it's perpendicular to 3, -2, -2. Now let's put on our hats. Okay. We start thinking. I now know that my gradient is perpendicular to two things. All right. How can I find something which is perpendicular to two things? Does anything cross the mind?
Cross product?
Yeah, cross product. Right. Good. Good. I sometimes it just does, right? So I'll go ahead and do a cross product really quickly here. So these aren't so bad. It's good to remember these. You're going to need these, by the way, definitely for the third exam. So it's good not to forget these. So just when you thought you were safe, you thought it was safe to go back in the water. No. All right. So if you work this out, let's see, you get a 2i and then nothing I. So that's 2 in the first slot. And let's see, j would be, I think, a 6 in the second slot. And k, I think, is a... No, that can't be right. All right, Steve, you got to be careful because everybody's watching you. Sorry, what? Negative 2i? Oh, yeah, you're right. Negative 2i. Okay, thank you. And the last slot should be -9, I think.
Yes.
All right. Now, of course, I should be paranoid because I screwed up my computation. And as a paranoid person, yes?
Is it -6 too? It's -6. So it's positive.
Now you're making me nervous. Okay, so
It's like the minus.
we should probably check. How do you check your cross products? Yeah, dot products. -6 plus 6 plus 0. That's good. Minus 6, minus 12, plus 18. All right, good. Now, question. Is this our gradient? No. But it's kind of almost the right direction. Now you're probably thinking, that's a really non-committal kind of almost. We'll get into that in a second. What are some things that we need to knock down? Well, we haven't yet handled this, 22. Let's check what the current magnitude is. What's the magnitude of -2, 6, -9? Well, that's the square root of 4 plus 36 plus 81.
11.
Which is 121, yeah? Which is 11. Oh my gosh, wow. It's like they planned it that way. So, I don't have the right length. See, currently it's length 11. I should have length 22. So what do I need to do to this? I need to double it. Okay, so now we have a candidate. Double this. -4, 12, -18. And at this point, you're probably thinking, well, what do you mean you have a candidate? Isn't that the answer? There's one other candidate. What's the other candidate? Yeah, if I just go in the exact opposite direction, that's a second candidate. Everything we've talked about so far is satisfied by these two vectors. And the things we've talked about so far is the two directional vectors being 0 and the magnitude being 22. What haven't we used yet? Yeah, the fact that there's this other directional vector where the direction is positive. We said, boy, that's really vague, but now that'll be enough to tip the scales. So let's figure out what the direction is. What's the direction from 132 to 615?
5, -2, -3.
5, -2, and what was it?
3.
3. So, the question is, don't worry about scaling, right? Scaling is just scaling. It's just a number, positive number. When I take the dot product of this vector with which one of these, which one will produce a positive output? Sorry, what? Right, 1 over something. Okay, so when you take 1 over something, yeah, it's not a pleasant number. But you're right. But the nice thing is this 1 over something is a positive number. And you take the dot product, which one is going to produce a positive number? Yeah, you'll see the one where I let my finger linger for a long time. As if to try to nudge you to think. That's right. I'm playing mind games too. Yeah, you see that the signs match.
Really quick, what's the 1 over something we're using there? Like, I get that it's to make the unit vector to do that, but we have to do that. Like on a test, for example, we have to plug that piece in there and then.
You can put it in. It won't really change anything.
Okay.
So, this has negative. This has positive in terms of dot product. And therefore, we can finally come to the conclusion, because we want it to have a positive directional derivative, it must be, that is our answer. So there's our gradient. So this is really, a lot of this is just testing you on understanding properties of the gradient. Now you might be familiar with the 3D forest problem. It's sort of a infamous problem. People think I wrote that problem. I did not write that problem. One of the instructors this semester wrote that problem. So it wasn't me. Well, it is Bartlett or Bassnett because those are the instructors this semester. We have narrowed it down. So, but anyways, that problem, a lot of people went away thinking this is a very mysterious thing. But at the end of the day, that problem was just testing you on, do you understand things about the gradient? And that's what it was asking about. So if you understand things about the gradient, because the gradient is super powerful, then life is good. And if you don't, you're in for some trouble. All right, so number 7, find the rate of change of the function f of x, y, z equals x squared y plus 3xz minus 5yz cubed at the point 1, minus 1, 1, in the direction pointing towards the point negative 3, 6, 5. After the last problem, this should be pretty quick. First off, rate of change. What's another way to say rate of change? Derivative. So rate of change is secret code for derivative. So our problem is asking us to take a derivative. And then we see the word direction. We start thinking, oh, derivative, direction, directional derivative, right? We start making those connections. And we're like, ah, cool. So that says our directional derivative, we just talked about that. That means we're going to take a gradient at our point, and we're going to dot it with our unit vector. So now there becomes two parts to this. Namely, what's our unit vector, and what's our gradient? And we can do them in either order, because they are somewhat independent of each other. Which part do you want to tackle first? Unit vector. Unit vector is oftentimes pretty straightforward. So we know where the start is, because we're at the point, and we're going towards another point. Sometimes the vector is given to you as an explicit vector. Sometimes it says from this point to that point. Sometimes they try to make it very mysterious. But usually it's nothing too bad. So first off, let's make a vector. So look at the change. How did we change to go from 1, negative 1, 1 to negative 3, 6, 5? Down by 4, up by 7, and up by 4. So that was how we changed to get from to get from 1, negative 1, 1 to negative 3, 6, 5. Is this our unit vector? No, it's pretty easy to see it's not a unit vector, because those are big numbers. So the next thing is, okay, we're going to take the magnitude of this, which is the square root of 16, because we're going to square each term, plus 49 plus 16. And we cross our fingers and hope that whoever wrote the problem gave us nice numbers. Oh, it's 81. That's a nice number, because that means it's 9. And so our unit vector will be 1/9 of negative 4, 7, 4. And you can leave the 1/9 out here. You don't have to multiply the 1/9 through each term. If you prefer to multiply the 1/9 through each term, that's also fine. All right, now that's just the half of the problem. We have to do the other half, which is the gradient. So first thing is, we're going to find the generic gradient. So it's partial derivatives. Derivative with respect to x, 2xy plus 3z. Derivative with respect to y, x squared minus 5z cubed. And derivative with respect to z, or z, if you want to sound very European.
3x minus 15z squared y.
3x minus 15 z squared y, or yz squared, if you keep in the same order. So what's next? Plug in your point. 1, negative 1, 1. Okay, well, this is slightly trickier than doing 1, 1, 1, but not too bad. You just got to be careful. So it's going to get minus 2, because of that minus there, plus 3. So the first entry is minus 1, plus 1. There we go. Right, minus 2 plus 3. Yep. Okay, next entry we're going to get 1 minus 5. It looks like negative 4. The last entry we're going to get 3 minus 15, but there's another minus 1 here, so that's really 3 plus 15, which is 18. So we have 1, negative 4, 18. Now, we're not quite done, but we're getting close. What's the next thing we need to do? Yeah, dot is something we should do. So I like to leave the 1/9 out in front, and then I just work through it. 1 times negative 4. It's negative 4. Negative 4 times 7. Negative 28. 18 times 4. It's the answer to many questions. 72. Yeah, I know. But it's not the answer to everything. 72. It's half a gross. Right? You guys are too young. You don't know what that means. Okay. So, Minus 4 minus 20. If you put those together, that's minus 32. Plus 72 gets us up to what?
30 something.
Yes, 3010. Also known as 40. Right? Because minus 32 plus 72. And yeah, 40. And so we get 40 over 9. And that's the answer. All right. So again, directional derivatives. If you see a problem that says directional derivatives, you should just be like, take the gradient, find your unit vector, take dot product, get the 10 points, and life is good. All right, number 8. Oh, we're making good progress. We're over halfway now. The relationship x to the fourth plus y squared plus z to the sixth equals 3xz implicitly defines z as a function of x and y. Use this to find partial z partial x and partial z partial y. Now, what's maybe the key word here in this problem? Implicit, yes. If you see a word that says implicit, that's a clue. Now, you might say, it's a clue to what? It's a clue to what technique you should be using. And we should be using, implicit differentiation. That's the right technique here. Now, the key here is it even tells us we want z as a function of x and y. So here's what's going to happen. You're going to be taking the exam, and you're going to be like, I see an implicit differentiation problem. And you're going to start having a thought. And you're thinking, oh, I know how to handle an implicit differentiation problem. That says, whenever I see z, I'm really going to think of that as being some function of x and y. So that's going to be there's going to be a little bubble, thought bubble floating right there. And you're going to be like, okay, I know how to handle this. And what do I mean by that? Well, what we're going to do is we're going to take derivatives. The problem tells us what to do, actually. See, it tells us take the derivative with respect to x, and it says take the derivative with respect to y. So we're going to take two derivatives. So the first thing is we'll start with the derivative with respect to x. So let's find out what happens. So this notation, partial x, means take the derivative with respect to x. And what we do is we're going to take the derivative of both sides with respect to x. So let's work through it. The derivative of x to the fourth with respect to x. 4x cubed. Derivative of y squared with respect to x. 0. Derivative of z to the sixth with respect to x. Now our thought bubble comes in. Oh, you're right. See, there's not an x explicitly written, but really this is z of xy to the sixth. So when I take the derivative of this with respect to x, I got to use the chain rule. So it'll be 6, the function z of xy to the fifth, and then what else do we need? By the chain rule. The derivative of the inside. What's the derivative of z with respect to x? The answer is, it's the derivative of z with respect to x. We don't know what it is. But we use the symbol for what it should stand for. On the other side, because we've got to take the derivative of both sides, what rule do we need to take the derivative of 3xz? Product rule, because there's two places x shows up. Again, this z, we're thinking about it, is really a function of x and y. So, what's the derivative? Okay, well, I'll think of 3x as the first function. The derivative of 3x is 3. That's no surprise. So 3z plus 3x. What's the derivative of z with respect to x?
dz dx.
It's the derivative of z with respect to x. All right. So we've taken the derivative of everything with respect to x, being careful to always remember that whenever we encountered a z, there was some function of x and y that we just didn't know. Now, we're not done yet, but we're very close. To finish off finding dz dx, derivative of z with respect to x, what do? Yeah, we get dz dx by itself. So we're going to move things around. So I'm going to move some terms around. If we do that, we'll get 6z to the fifth minus 3x times derivative of z with respect to x is equal to 3z minus 4x cubed. And now divide. So dz dx, derivative of z with respect to x, is 3z minus 4x cubed. Divide that by 6z to the fifth minus 3x. Now the good news is, if you didn't quite catch that, we're going to get to do this all again. So, hopefully round 2 will go even better. So what's round 2? Well, we read what this says. The denominator tells us what derivative to take. So we see a partial y means derivative with respect to y. So we're going to take the derivative of both sides with respect to y. Derivative of x to the 4th. Gone. X and y are going to be thought of as independent. So they're the free choices. It's z that depends on x and y. Okay, how about the derivative of y squared?
6z to the 5th.
Well, y squared?
Oh, 2y.
2y. Right. But now we'll come to the derivative of z to the 6th. What is that?
6z to the 5th.
6z to the 5th times the derivative of z with respect to y. All right, on the other side, 3xe. What rule do we need? It's just nothing fancy, right? 3x, how do I treat it? It's a constant. So it's 3x. And what's the derivative of z?
dz dy.
Derivative of z with respect to y, dz dy. Okay, so we move stuff around. And we'll get that 6z to the 5th minus 3x times derivative of z with respect to x equals minus 2y. And so, with respect to y, thank you. So derivative of z with respect to y equals minus 2y divided by 6z to the 5th minus 3x. And that's our answer. Okay, just remember to have that thought, and then life is good. All right, number 9. This one's a fun one. It's actually pretty, this came from an old exam. Another one that came from a very old exam in the dark ages. So, we have a function which is everywhere differentiable and has this strange thing. F of t squared minus 2t comma e to the t minus t equals this really bizarre expression, e to the 3t minus sine of 2t plus t squared. There is exactly one point for which f sub x of ab can be determined, and exactly one CD for which f sub y of CD can be determined. And we want to determine them. Now, when we say that that's exactly one, that just says using only the information given here. Now, if we had more information, we might be able to determine more. What kind of problem is this? Chain rule. How do you recognize chain rule? Yeah. When you see functions inside of sort of our slots, when you see functions inside of functions, another way to recognize chain rule, it doesn't apply to this problem, but another way to recognize chain rule is if it says chain rule. So, look out for that. Now, what should we think of? Well, what we really have here is we usually think of this as a function, I'll call it x and y. Then what we have is that x, it's really a function of t, which in this case is t squared minus 2t, and y, well, that's a function of t again, and it's this function e to the t minus t. So the diagram we have is that f depends on our variables x and y, and that x and y depend on our variables t. I find it useful to draw a diagram because it helps me sort of say, how do all the variables relate? Now, diagrams can be more complicated. There's all sorts of things that can happen, but if you say, how does this function depend on other functions? And then you work your way down until you get down to your variables. So, well, now what we can do is we can say, okay, really at the bottom of this is we have t's. So I can talk about what's the derivative with respect to t. So if I ask the question, what is df dt? Well, if we use the diagram, let's not worry about this part yet, what can we say? Look for all the ways to get down to t. Now let's suppose I come along this route, f through x through t. Okay? This edge right here says, hey, f depends on x. So I look at partial f, partial x. This says x depends on t, and I'll use a dx dt. Now, you might wonder, why do you use a partial there, but a d there? Do you remember the answer to that? When do you use a partial versus when do you use a d?
Multiple variables?
Yeah. How many variables? X depends on just one thing. If you ever have a function depending on one thing, it's a d. If you have a function depending on multiple things, it's a partial. And the truth is, we're usually not that too persnickety. I think that's a word, persnickety. But, well, hopefully it was before too. All right. So what do we have? Well, through that route, the left-hand route, we have that it is partial f, partial x, dx dt. And that's not the only way that we have t showing up. There's a second route, the right-hand route. So we see that f depends on y, and y depends on t. So we get a second option, and we add them together. Partial f, partial y, dy dt. You should be comfortable with drawing a diagram. You should be comfortable with writing the equation. Because if you can do that, you're a good chunk of the way to understanding what to do next. Now, in our case, we don't know what f is, so I can't talk about partial f, partial x. But I do know what all the functions of t's are. So, for example, do I know what df dt is? Yeah. There's my function of t. So I can take the derivative of that. So what's this derivative? 3e to the 3t.
Minus 2 cosine 2t.
2 cosine 2t plus 2t equals partial f, partial x, which I don't know anything about, times dx dt. Well, there's our x. What is dx dt? 2t minus 2. And be careful here. This parenthesis is not indicating I'm plugging 2t minus 2 in. It's just this is a multiplication. Plus partial f, partial y times dy dt. Well, what's the derivative there? e to the t minus 1. All right, now we take a look at this and we start thinking to ourselves, I want to find an f sub x at some place. Which means if I want to find f sub x, I don't want to have any f sub y terms showing up. So we start thinking, is there any good choice for t which would knock out that expression? 0. And that's our great, so at t equals 0, we plug 0 into both sides. What happens? Well, we get, on here we'll get 3 minus 2 plus 0 equals partial f, partial x. At some point, I'll actually talk about that point in a second, times negative 2 plus partial f, partial y at some point times 0. Well, times 0 is hard to recover from. What goes into the point? How do you find that? Well, yeah, so this is, where are we at time 0? So we plug it into our x and y. At time 0, where's our x value? 0. At time 0, where's our y value? 1. And so we're like, we've knocked out the partial f, partial y. We have partial f, partial x at 0, 1 times negative 2 equals 1. So we can come to the conclusion that f sub x at 0, 1 is equal to negative a half. All right. But we're not done yet. We said, well, we'd like to knock out the f sub y term, but we could also knock out the f sub x term. What would do that? T equals 1. So now we plug in t equals 1. Okay, so what do we get? Well, we get 3 e to the 3 minus 2 cosine of 2 plus 2, which simplifies to, doesn't, no, that's just it. All right, sometimes that's just the way it is. Partial f, partial x at some point times 0 plus partial f partial y at some point times, and what will we get? E minus 1. Now, the times 0, hard to recover. That's going to go away. Where's our point going to be? What's our x-coordinate? Negative 1. What's our y-coordinate? E minus 1. So, last thing to do is divide. So we can say that f sub y at negative 1 comma e minus 1 is equal to 3e cubed minus 2 cosine of 2 plus 2 divided by e minus 1. Exactly what we would have thought. No. We never would have guessed that one. But we didn't have to guess. We have the tools. And the tools will help us solve the problem. Okay. All right. Good. Number 10. Given that f of st is 4e to the power 2s minus 5t plus t squared minus 3s, use linear approximation at the point 5, comma 2 to estimate f of 5.1, comma 1.95. Now, when you hear the word linear approximation, what do you replace it by? Tangent plane. Tangent planes are linear, which is another way of saying a tangent plane is a flat thing. And it's an approximator in that the tangent plane mimics the function. So what's happening here, whenever we see something that involves a linear approximation, it says, find the tangent plane to your function and use the tangent plane and see what happens at the point nearby. So that's how these problems go. So maybe the only thing that's strange is instead of using the symbols x and y, it's using s and t. Does that change anything fundamentally? No. It's still the same processes. It's just different symbols. Now, if you're really uncomfortable, just say, look, I'll go ahead and just change it to x and y because, hey, it's a free country, and I know that it's going to be the same process. So if you're more comfortable, you can do it and say, look, this is the same process. These are just symbols, and life is good. If you're okay keeping it as s and t, that's great too. Whatever makes you happy. Because we want you to be happy. We want you to enjoy these tests. We want you to walk out smiling and be like, wow, what a great test I just had. All right. So, tangent plane. This is our function f of xy. So hopefully your neurons remembered it from earlier today. Function at ab. I'll go ahead and use x here. F sub x at ab times x minus a. F sub y at ab times y minus b. So, we need to take our partial derivatives. Derivative with respect to x will be okay, 8 e to the 2x minus 5y. Anything else? Minus 3. Okay. F sub y. Negative 20 e to the 2x minus 5y, and then 2y. Okay, so we're almost there. So we start plugging things in. So we plug in 5, 2. Let me just work our way through. So plug into our function first. We'll get 4 times e to the power 10 minus 10. So it's really e to the 0, which is 1. Oh, wow, what a good choice they made. Plus the y squared, which is 2 squared, which is 4, minus 3 times 5, so minus 15. So that's 8 minus 15 is negative 7. So that's going to be the function, negative 7. F sub x at 5, 2. Well, we're going to get 8. And again, it's e to the power 10 minus 10. So again, it's still 1. Subtract 3. Gives us 5. So that's the next term, 5. F sub y at 5, 2. Well, minus 20, that's a big number, e to the 0 again. Then plus 2 times y, so that's plus 4, so that's minus 16. So that's the term there. So we have our tangent plane is minus 7 plus 5 times x minus a. Well, that's our AB is 5, 2, so that's x minus 5 plus negative 16 times y minus 2, because b is 2. Don't try to simplify this. In other words, don't expand it, because that's actually going to be detrimental to what we want to do next. So this is our tangent plane. Now the moral of the tangent plane is that the function, it's a pretty good approximator. So in other words, the function is approximately what the tangent plane is. That's the whole idea of linear approximation. So all I'm going to do is, instead of saying the tangent plane, which is z, I'm going to replace that by saying, well, it's about the function. So f of xy is approximately what we just found. Our last thing to do is plug in the point that we were given. So f of 5.1 comma 1.95. Well, so that's negative 7 plus 5 times 5.1 minus 5, which will be 0.1, which is easy to work with, at least easier-ish, minus 16 times 1.95 minus 2. Negative 0, let's see, 0.05. Okay, so 0.5 times, 5 times 0.1 is 0.5, so we get negative 7 plus 0.5. Now this one, minus minus makes a plus. Let's take 16 times 5 first. 16 times 5. 80. Now we got to account for the fact that our decimal place has been moved over by 2. So instead of 80, it'll be 0.8. So just move the decimal over 2 times. Well, we can actually finish this up. So 0.5 plus 0.8 is 1.3. So if I take negative 7 and I add 1.3, what will I get? Negative 5.7. And that is our estimate. Of course, that's probably not what the function is, but it's an estimate. So, all right. Any questions? Yes?
Is there any case where this would be quicker than just using the gradient to solve for it?
It's about the same amount of work, to be honest with you, because what you're doing here is these are the gradients. Yeah. But you have to sort of understand, if you're using you have to be a little bit careful. But yeah, this really, almost everything is the same thing. It's not like we have chocolate ice cream one day and vanilla ice cream the other day. It's like, okay, today is vanilla, tomorrow is French vanilla, the next day is vanilla bean. It's we have like one tool and we keep calling it like 10 different things. Yeah, so it's about the same amount of work. The thing is, we do not want to force you to follow into certain lines. If what you do is correct mathematically and follows the guidelines of the problem, you should get the points. Now, the reason I add the phrase follow the guidelines of the problem is that sometimes we'll specify using such and such a technique. But if it doesn't force you to use a certain technique, use whichever technique you feel comfortable with, as long as it's mathematically justifiable. All right. This is good. I like this. We're getting close to our classification stuff. Optimization is around the corner. But before we get there, Taylor polynomials. Okay, so we have a function, and we want to write the second order Taylor polynomial for this function at the given point 1, 2. So let's remind ourselves how Taylor polynomials work. So if I have a function, the idea of a Taylor polynomial says, let's approximate the function. Now, we just did that. Well, but that was a linear approximation. And essentially what linear approximation says, let's use information up through the first derivatives to try to do our best to figure out what the function behaves like. Taylor polynomial says, why stop at the first derivatives? There's so many more derivatives out there. You could go to second derivatives. We're like, okay, we'll go there. And of course, Taylor polynomial will say, how about third derivatives? And we say, no, we're good with 2. So you have to be able to do second order. You won't have to do third order. So what does the second order Taylor polynomial look like? It looks like the following. You have your function at your point plus your first derivative, f sub x, ab, times x minus a, plus f sub y at ab times y minus b. If I were to stop there, you'd say, yeah, that's what you just talked about. And it is. That's your linear approximation. Second order says, now go into your second derivatives. fxx at ab times x minus a squared over 2. The reason you need that over 2 is you're going to take this derivative twice, and when you take this derivative the first time, you have to compensate for the 2 coming down. Plus fxy at ab times x minus a y minus b plus fyy at ab times y minus b squared over 2.
Is this something we're given?
Sorry, what?
Are we given this, or is this a brain?
Yeah, your brain is good. You guys are young. Just, if worst case scenario, just rederive it. It only takes like 15 minutes. Tops. You know, you've got some spare time. You've got time. I mean, the first half is pretty straightforward. It's like, hey, it's the tangent plane. Woohoo! I remember that. I already stored that in my neurons. And then it's like, well, okay, now I need all the second order derivatives. And it's just like, if I take 2 derivatives, you know, so if you look, it's not so hard. See, like xx, that means I need like an x squared. See that xy? I need like an xy.
Where does the over 2 come from?
Okay, so the over 2 comes from when I take 2 derivatives, I want to get just this term out. So what happens when you take 1 derivative?
You just had it?
Well, the 2 comes down, right? The first time you take a derivative.
Oh, okay.
So you gotta cancel that 2 that came down. So that's why I need that over 2. See, here there's no like powers that need to come down to get canceled. That's why there's no over 2 here. So.
Shouldn't there really be a 2 out front on that fxy? But it's canceled, divided by 2 and it's canceled.
You can think of it that way. If you want, you can write a 2 over 2 if that helps you. So, you can actually write it in the following way. You can write it as 1/2 fxy ab x minus a y b plus 1/2 fyx ab x minus a y minus b. That would probably be the more correct term. Which, this is easier for me to remember. I'm old. I got to start conserving. You know, I don't even remember, all the names of the characters from One Piece anymore. It's hard. It's hard. Okay. So, how does this problem work? Well, the good news is we don't have to do anything with the polynomial. We just have to write it. Now, sometimes you may have to do something with the Taylor polynomial. And you might say, well, what's something I could do with it? Well, the answer is, you just think about what we just did. We can approximate using a tangent plane. We can also approximate using a Taylor polynomial. So you might see that type of problem, approximation with a Taylor polynomial. But for now, we just need to write it, which means we have to fill these slots in. And by the way, AB is 1, 2. So most of this problem is just going to be, let's take derivatives. So we have our function here. I'll give some space so we can work here. Our function, fxy, that's 2e to the 2x minus y plus x squared minus 3xy minus 2y. So what does f sub x look like? All right.
4e to the 2x minus y plus 2x minus 3y.
Yep, 4e to the 2x minus y plus 2x minus 3y, fy. minus 2 e to the 2x minus y minus 3x minus 2. First order derivatives, no big surprises. fxx, and in the interest of time, because we have some fun problems coming up, 8e to the 2x minus y plus 2. fxy minus 4e to the 2x minus y minus 3. fyy is 2e to the 2x minus y. Any one you want to talk about? A lot of this is not surprising. It's really just be patient, be careful, take your time. You've got time. You got 75 minutes, 7 problems. That's like 10 minutes per problem. And that still gives you 5 minutes left over to sort of stare at the proctor. And so, plenty of time. Plenty of time. Now, we're not done yet. Now, some people just say, okay, let me start putting these things into the various pieces. But that's wrong. These should be numbers, not functions. You got to evaluate. Don't forget to evaluate. So the next thing is, after you do all this computation, is to evaluate at your point. So you get your f at 1, 2, your f sub x at 1, 2, your f sub y at 1, 2, your fxx at 1, 2, your fxy at 1, 2, and your fyy at 1, 2. Now to help us, we should point out what happens to e to the power 2x minus y, because that keeps showing up. E to the power 2x minus y at the point 1, 2 becomes 1.
Yes.
So, good news. It simplifies. So we get 2 plus 1 minus 6 minus 4. So that's 3 minus 10, negative 7. Next line. 4 plus 2 minus 6. 0. Good. That's our favorite number. Minus 2. Then we have minus 3. And then minus 2. Very negative. Negative 7. fxx. 8. Plus 2. Makes 10. fxy. Negative 4. Minus 3. Negative 7. fyy. 2. Which is 2. Probably that last equals 2 was redundant, but it just felt right because I've done it on all the others once. All right. Are we done now? No, but we're so close. We really are. The next line that we write down will finish it off for us. So our last thing is to say we just start filling things in. So f of ab is negative 7. F sub x is 0, so we don't need that term. F sub y is minus 7. Then we're going to times that by y minus b. So in our case, b is 2. Then we have our fxx. That's 10. We're going to divide it by 2, so I'm going to make it a 5 times x minus 1 squared, because x minus a is x minus 1. Then fxy is minus 7, x minus 1, y minus 2, x minus a, y minus b. And the last one is fyy, that's 2. There's an over 2 here. So that will just become a 1 times y minus 2 squared. And that is our answer. It's written out kind of long because I just want to write it underneath, this matches with that, matches with that. If you write a little bit more compressed, which is probably what you would do on a test, minus 7 times y minus 2 plus 5 times x minus 1 squared minus 7 x minus 1 times y minus 2 plus y minus 2 squared. And that's it. We're done. All right, 3 problems left. Well, you know what's coming. We're doing optimization week, right? And there are 3 flavors of optimization. So let's talk about them. Number 12. Find and classify the critical points for h of xy equals 2x squared y minus xy squared minus 2x squared plus x plus 17. Now, the key word here, there's one word that if you see it, you automatically know what type of problem you're doing. Do you know what the key word here?
Classify?
Yes. If you see a problem that says classify, you know exactly where you're at. So classify, that should trigger the following reaction. It says, okay, I'm in the place where I need to do the second partials test. So there's two stages to these problems. There's the find stage and the classify stage. The find stage is the hard stage. So let's do that one and just bite the bullet. So when you're finding, the way you find is you take your partial derivatives and you're going to set these to 0. So you set h sub x equals 0, h sub y equals 0. This will never be a function of 3 variables. This will all be a function of 2 variables, 100%, because you do not have the tools to classify functions of 3 variables. We haven't taught you that. That's multivariable calculus. Here with respect to x, what do we get? 4xy minus y squared minus 4x. Wow, that's a long expression. Derivative with respect to y, what do we get? 2x squared minus 2xy. A much better expression. Okay, now we start putting on our caps. When we're doing the find stage, there's only a handful of tools we should be thinking about using. What are a handful of tools? They're simple. There's factor, there's substitute, and there's combine. That's it. That's pretty much our tools. More or less anything you do is something that relates to one of those ideas. So factoring means you factor both of your equations. Substitute says I solve for a variable in one and plug it into the other. Combine says if I multiply the first by something, add it to the second, I get cancellation. I like factoring. Factoring is just so cool. So I always cross my fingers and say, does anything factor? Yes. Which one factors? Yeah, it's kind of hard to miss the second one factoring because it only has 2 terms. How does it factor? 2x times x minus y. And remember, this equals 0. And here's the power of factoring. If I have 2 things multiplying and they equal 0, what must be true about one of those things? One of them has to be 0. It's not possible that it's anything else other than that. So we come to the conclusion that because this is equal to 0, this is going to force to either have x equals 0 or x equals y. Now, it's not that I have both. I have one of those two. Now you might say, okay, how do you use that information? Now, you go back to the first equation. Let's suppose for a second x equals 0. Rewrite the first equation using that information. Well, anything with an x goes away, so you get the first equation says minus y squared plus 1 equals 0. What does that tell us about y? Well, what could y be? Plus or minus 1, right? So that tells us if we see that x equals 0 from the second equation, y has to be positive 1 or negative 1 to make the first equation also true at the same time. Which leads us to a point 0, 1 and 0, minus 1. So those are 2 critical points. And that's if we go down the x equals 0 path. But we don't have to go down the x equals 0 path. We could go down the x equals y path. But the process is similar. Come into here, and let's replace every occurrence of x by a y. Or you could replace every occurrence of y by x, just whichever one makes you happy. So 4y squared minus y squared minus 4y plus 1 equals 0. This would become 3y squared minus 4y plus 1 equals 0. Well, what do we hope? We hope it factors. And does it factor? I'm going to pretend like it does. I actually don't know. I didn't do this one in a long time. Well, first off, the 1, there's not a lot of stuff to do there. So the only way you can break 1 up is as 1 and 1. And 3, there's not a lot of ways to break 3 up. So it would have to be 3y and y. And then the question is, what should the signs be? Well, they better both be the same because of the plus. And if they're going to both be the same, they both better be negative because of that minus. Now we just check. 3y squared, yep, that works. Minus 3y minus y, that's minus 4y. And minus 1 times minus 1 is plus 1. So what does that tell us about y? 1/3 or 1. What does that tell us about points? Well, 1/3 of 1/3 and 1, 1. Which means you get 1, 2, 3, 4 points. 4 potential points. Okay, so that's the find stage. That's the, I like to think of that, that's the hard part. So let's talk about classify. Now to classify, we just have to remember the rule. So the way that the rule works is we're going to compute something, we call it D, which is hxx, hyy minus hxy squared. It's a combination of the second partial derivatives. Well, what happens? Well, if D is positive, that means it's a min or a max. But that's not enough to come to a conclusion. You look in a slice, and usually the way we look in a slice is we look at hxx. And if that's also positive, what are we? Do you remember? If hxx is positive, so what we're doing is we're going back to our think of the second derivative test for Calc 1. If our second derivative is positive, our curve looks like that, which means we've got to be a min. If our second derivative is 0, our curve has to look something like that, which means we're at a max. And if our second derivative is 0, we have no idea what's going on. Okay, so D is positive, hxx is positive, min. D positive, hxx negative, max. D negative, saddle. That happens a lot. If D is 0, yeah, we just stop. Yeah, inconclusive, we make no decision. We're not here to judge people. No, that's not what we say. But we say, just stop. We don't know, inconclusive. So now what we need to do is actually, for each one of these 4 points, we've got to compute this value. So let's figure out what D looks like. So what is hxx? 4y minus 4. Hyy?
Negative 2x.
Negative 2x minus hxy. 4x minus 2y, and then, of course, squared. All right, so let's plug in some points. If we plug in 0, 1. So at 0, 1, what happens? Well, notice x is 0. That's going to knock out the term, the hyy term. So then the first part is gone, minus, then we have 0 minus 2 squared. So D at 0, 1, oh sorry, I probably should write this. D at 0, 1. I actually don't care about the value. Don't get caught up with the value. What do we care about? We care about the sign. It's positive or negative? Negative. So what does that tell us about 0, 1? Saddle. Back in the saddle again. Now, what if I do 0, negative 1? Similar thing's going to happen. See, that 2x is going to knock out the first half. Then I'm going to have minus something squared. So that's negative still. So 0, negative 1 is a saddle. All right, Maybe we'll do the 1, 1. If I put in y equals 1 here, what do you see?
0.
See 0. So the first half is gone again. Minus something squared. So what is d11? It's negative, which means this is a saddle. We have had it before where we've had like 4 or 5 points and they were all saddles. But let's hope something interesting happens. Okay, something interesting, something interesting, something interesting. All right, d 1/3, 1/3. Let's see what happens. Well, you get 4/3, subtract 4, which is? Negative 8/3. Okay. Well, we'll write that down. Maybe we need to know that. Minus 2 times 1/3. So negative 2/3 minus. Okay, then we're going to get 4/3 minus 2/3. That's 2/3 squared, right? So let's see, that's 16 over 9, because minus 8 times minus 2 over 3 times 3, minus 4 over 9. Well, that looks positive to me. Ah, interesting. Okay, so it's not a saddle. But what is it? Look at your second partials. What's their signs?
Negative.
They're negative, so that means we are a max. And there we go. There are our critical points and their classifications. All right, number 13. Let R be the triangle with vertices at 0, 0, negative 3, 3, 3, 3. And we want to find the absolute minimum and maximum values of x squared plus y squared plus 2x minus 4y plus 4 on our region. So we have a vertex at 0, 0, a vertex here at 3, 3, and a vertex over here at negative 3, 3. All right. So there's our region. So, keyword here. What's the keyword? Well, what do you think? Keyword? Maximum is good, but there's something else that's also key. The absolute. If you see absolute, then you know you're in a very particular type of problem. Now, what type of problem is this? Well, this is the one that there's a song for. Because you were saying, if only we had a song, I could memorize this. What's the song? It goes like this. We're making a list, checking it twice, gonna find out which points are nice. Absolute, max, and min are found. Now, what does that mean? So, for problems like this, we know there has to be one. So our goal is to find where it could be. So we make a list. Now, when we're making a list, the way we make our list is we make sure we have corners, we make sure we have our interior checked, and we do our boundary edges. So we're going to make a full list of points which are interesting. After we've made that list, we're going to test each point on our list, and then we're going to come to a conclusion about which one's the largest or smallest. So we start making our list. Corners, we just throw them in as freebies because we need to have them there. All right, the interior. How do you check the interior? Well, the interior means gradient equals 0. So that's another way of saying partial derivatives equals 0. Partial derivatives with respect to x, 2x plus 2 equals 0. Partial derivative with respect to y, 2y minus 4 equals 0. And what do we end up with? Is there any point which satisfies both of those equations? The point -1, +2. Right? Now, you should check. We come now and ask the question, is -1, +2 in our region? Because if we had found a point over here, we don't care. But we found a point over here, which is on the inside. So it makes the list. Now, the fun part, the boundary. And this is why these problems can be fun, extra fun. For every piece of boundary, you got to do its own problem. We have 3 pieces of boundary. So we get to do 3 quick optimization problems. Now, what are our 3 pieces of boundary? Well, what is this line? It's y equals x. How about this line? Y equals -x. How about up here? Yeah, whoa, that one was quick. All right, you're good with the flat stuff, I see. It's the slanted stuff you got to work on. All right, y equals 3. So we're going to go through and do each one of these lines. Y equals x. Now, when I say do it, we're going to rewrite our function to be a function of one variable. So we're going to replace f of xy by f of xx. So everything's going to be in terms of x. X squared plus 2x minus 4x plus 4, which becomes 2x squared minus 6x plus 4. Take the derivative. 4x minus 6 minus 2x. Yes, take the derivative. 4x minus 2, thank you. 4x minus 2, set equal to 0. X should be a half, which means we're at a half comma a half. So that's the point. So that's the process of doing the boundary. You say, let me write my boundary curve as a function. And now instead of f of xy, where I have 2 variables, I can knock it down to 1 variable, and then I apply Calc 1 tools. Y equals minus x. So f of x comma minus x. So that's x squared plus 2x plus 4x. I think this time I'll get something right, hopefully. 2x squared plus 6x plus 4. We're going to get 4x plus 6. So that equals to 0. So x equals -3/2. -6/4. Which translates into the point -3/2 comma +3/2. So that's roughly over here. So we're up to, if you're doing a count, we had our 3 corners, our interior point, and we found 2 of our sides. 1 more side to go, which is the top. So y equals 3. So we have f of x comma 3, which becomes x squared plus 9 plus 2x minus 12 plus 4, which is x squared plus 2x plus 1. Oh, that's not so bad. Take the derivative, 2x plus 2, set it equal to 0. X is -1. So that's that point right there at -1 comma 3. All right, so you make the list. The list is where all the places where the absolute max or absolute min could occur. You sort of should double check, did I catch everything? Did I get my corners? Did I get my interior? Did I get all my bounding curves? What comes next? Plug it in. So we are going to plug every single point into our function. And this is why we usually tend not to put this on very often, but we have. Last semester we had one of these. So we got to be ready for it just in case. So f of 0, 0 is really simple. F of 3, 3, that's 9 plus 9, which is 18, plus 6, which is 24, minus 12, 12, plus 4, 16. Minus 3, 3, that's 9 plus 9, 18. Minus 6, which is 12. Minus 12, which is 0. Plus 4, which is 4. Minus 1, 2, you get 1 plus 4, so we're up to 5. Minus 2, that's 3. Minus 8, that's negative 5. Plus 4 is negative 1. A half, a half. Now, I recommend, instead of using this formula, you can actually say, look, a half is along the line y equals x. So we actually have this sort of somewhat simpler formula. 2x squared minus 2x plus 4. So a half squared is a fourth, times 2 is a half, minus 1 plus 4. So a half minus 1 is minus a half plus 4, would be 4 minus a half, which is 3.5. Minus 3 halves, 3 halves, so I can come here. So minus 3 halves squared, that's 9 fourths, times 2, that's 9 halves. 6 times minus 3 halves is a number. Okay, now we probably should actually talk about that. So 9 halves, this would become a minus 9. So this is combined to give you minus 9 halves plus 4, which makes this a negative 0.5. Negative 1 comma 3. Well, plug in negative 1 here. You'll get 1 minus 2 plus 1, which is 0. Okay. That's the part you should be really careful with your checking. But I'm just going to go on faith right now that this is correct. The last step for this problem is to do what? Well, there's no classifying. No classifying happens in absolute min or max. Now, you said we found the places where it could be. We found the values for the functions at those places. We're looking for the largest one. So we scan our list. Which number is the biggest number? 16. So this is our absolute max. And we also scan looking for the smallest number. Negative 1. This is our absolute min. And that's how the problem works. All right. And I know we're running a little bit late, but let's just do the last one because, you know, it's nice to have everything completed. Okay. This looks intimidating, which usually is a sign that it must be very simple. Now, to add to the complication of this problem is the fact that we haven't actually learned the technique here. Because if you scan ahead, it'll tell you, use the method of Lagrange multipliers. So, we haven't talked about that in many classes, but we will next week. So, I'm going to quickly tell you what the method of Lagrange multipliers is. We're going to make it very quick. It's very simple. The goal is you want to optimize a function of x and y given a constraint. And usually the constraint takes the form of gxy equals some value c. So it's called constrained optimization. So it's not that I want to optimize over arbitrary x and y. I want to optimize over specific x and y. How does it work? And the answer is you introduce something called the multiplier. And the key, it's actually a beautiful idea. It says the partial derivatives for the two functions should be multiples of each other. So f sub x equals lambda g sub x, f sub y equals lambda g sub y. You set that equation up, and now here's the key. We don't care about lambda. So solve for lambda to get a relationship for x and y. If you do that, 95% of the time, that'll get you through the problem. Now you might say, well, that's just a relationship for x and y. How does that help me? Because one relationship is not enough. Do I have a second relationship? The constraint. So I have two relationships for x and y, which gives us two equations, two unknowns, solve for x and y, and you're done. So let's demonstrate it. So this is a long problem, so I'm going to sort of quickly hit the highlights. You're on a special episode of the reality TV show, The Ultimate Extreme Happy Fun Roller Coaster Happy Fun Hour. Oh man, there's happy fun is twice. That's lots of happy and fun. Okay, you're in the third round called blackjack. You have to be the fastest to gain exactly 21 points. And you do it by taking two different types of roller coaster rides. There's something called the extreme tumbler and the why won't it stop. Now they take different lengths of time, and the points, they aren't sort of normal. That's weird because it's, reality TV. So if you ride the extreme tumbler X times and the why won't it stop Y times, your total score is this equation 2xy minus 3x. So you can tell that most of this is not important, but whenever you see like, a math formula, it's like highlight. As you watch the contestants going before you, you can't help but notice that they're dazed, maybe confused as they switch the ride, slowing them down. And in particular, the total amount of time the contestants ride the two roller coasters is another equation, 2x plus y plus 3xy. Sorry, 2x plus 3y plus xy. So the problem, use the method of Lagrange multipliers to determine the optimal number of times to ride the two roller coasters together to gain 21 points as fast as possible. Which one of these two are we trying to optimize? We are after making fast, which means we're after time, which is the second equation. So we want to optimize 2x plus 3y plus xy. Well, where is the first equation? Well, that's our points. Remember, there was another number we didn't highlight. We should have. We need to get exactly 21 points. So that's our constraint. So we need to have 2xy minus 3x equals 21. Okay. So here we go. Again, this is our f, what we're trying to optimize. This is our g, what our constraint is. What is our f sub x? Well, it would be 2 plus y. Yeah, no worries, no worries. Equals lambda g sub x, which is the 2y minus 3. Okay. F sub y. Three plus x. That equals lambda times g sub y, which is 2x. Okay, so we start by setting up the fx equals lambda gx, fy equals lambda gy. Now, follow the rule of thumb. When I teach this topic in a longer class, I say, when in doubt, solve for lambda. And we are often full of doubt. So, lambda, here I would divide. So I'd say 2 plus y divided by 2y minus 3. But I could also have taken the second equation and solved for lambda. That would be 3 plus x divided by 2x. So that's what I mean by solve for lambda. I just take both equations and get lambda by itself. Now forget about the lambda, because the lambda is not important in the answer. You don't care about lambda. It's the x and y that are important. What would you do next? Cross multiply. Get rid of fractions. Fractions have been our enemy for a long time. So we've learned to deal with them in ways of how do we get rid of them. So 2 plus y times 2x equals 3 plus x times 2y minus 3. Now what happens? Okay, so expand out using our algebra. Algebra. Algebra will help us solve the problem because it's algebra. All right, sorry. Anyways, I was just getting carried away there. It's easy to do when you're talking algebra. 4x plus 2xy equals 6y minus 9 plus 2xy minus 3x. And you're probably like, oh boy, that looks terrible, Steve. Why are you doing this? But wait a second, it's not all terrible. There's some good news. What's the good news? 2xy's cancel out. That's great news. We get, if we move the the minus 3x across, 7x equals 6y minus 9. So that gives us a pretty good relationship between x and y. But remember, we also had this other constraint. So we can either solve for x or solve for y. Which one do you want to solve for? Solve for x? Yeah, we might as well. I mean, solving for x is really quick right here, right? Because you just divide by 7. X equals 1/7 times 6y minus 9. Now we can take this. This helped us get a relationship. We plug into our constraint. You're right, we should have solved for y. Well, okay, you live and learn. All right, so 2 times 1/7 times 6y minus 9 minus 3 times 1/7 times 6y minus 9 equals 21. Well, let's go ahead and multiply both sides by 7. 2 times 6y minus 9. I forgot a y somewhere. Oh, yes, there's an extra y here I forgot. 2xy times y minus 3 times 6y minus 9 equals 147. You're probably getting nervous. I don't blame you. I am too. But let's see. We persevere. Multiply it out. 12y squared, 2 times 6y times y, minus 18y, minus 18y, minus 9, and bring the 147 across, minus 147 equals 0, which is 12y squared minus 36y minus 156. Oh dear, oh dear. We just have to factor that. But can we do anything?
Did you forget to multiply the -3 times -9?
Didn't I forget to multiply the -3 times -9? That sounds like something I would do. So, it's good to have people checking. So that's minus 27, so that's not minus 156, that's minus... It's minus something.
Should it be positive 27?
Oh, positive 27. Yeah, my gosh. Yes. Wow. Shh, don't tell the other students I did this. So, that'll be minus 120 then. Okay. So this is looking terrible, but it's not looking so terrible because what can you do? You can divide by 12. Everything's a multiple of 12. So, we just got that little space left. Y squared minus 3y minus 10 equals 0. Can that factor, y squared minus 3y minus 10? That'd be great if it does. Does it? Yeah. Y minus 5 and y plus 2 equals 0. So what does that say about y? 5 or negative 2. Well, can we write it? Can we take a roller coaster a negative number of times and write it? Yes? No, we can't. So we can actually rule it out. Now, that says we should have, in our final answer, y should be 5. How do we get x? Plug 5 in. 6 times 5 is 30. 30 minus 9, 21. 21 divided by 7 is 3. So we should ride the extreme roller coaster 3 times. The y won't stop 5 times. And speaking of why won't it stop, it feels like this review, but actually that's the end.